Hello and welcome to the final session of the Fluid-Structure Interaction course. There will be two videos in this session where we will discuss the interaction between a structure and a flow having its own dynamics. As a reminder, we have categorized the fluid-structure interaction problems by comparing the respective orders of magnitude of the reduced velocity and displacement number. U are very small compared to D for the fluid at rest, U are very large in front of D for the aeroelasticity, and U are of the same order of magnitude as D in the case of strong coupling. Last time we studied the strong coupling with the potential flow. This time we will look at some cases of coupling where the flow has its own dynamics. In this video 6.1, we will look at the very common case of interaction with a vortex wake, whereas in the next video we will highlight transient dynamics in the flow around profiles and their influence on the dynamics of a structure. We start by studying the interaction between a structure and a vortex wake. We will highlight a phenomenon called vortex-induced vibration. Before tackling the interaction with a vibrating structure, let us see what are the properties of the wake created by the still object. In particular, we will look at the case of the cylinder. Let us look at what happens when we increase the flow velocity. As the Reynolds number increases, the flow regime undergoes different transitions that we will describe. For small Reynolds number, that is for Reynolds less than 4, the flow is stationary and dominated by viscosity. The streamlines go around the cylinder and we observe upstream-downstream symmetry. At Reynolds equals 4, this solution of the Navier-Stokes equation still exists, but it becomes unstable. Another stable stationary solution appears in which a recirculation zone exists downstream the cylinder. This solution remains stable until the Reynolds number reaches the value of about 40. At this value, the solution with recirculation becomes unstable and a periodic vortex detachment appears. This vortex wake is called the von Karman wake. At higher values of the Reynolds number, the vortex detachment continues to be observed with an additional recirculation zone behind the cylinder. Then, the vortex wake becomes progressively turbulent. This progressive transition takes place up to a Reynolds number of about 400. From this value, the von Karman wake is fully turbulent and this regime persists until a Reynolds number equal about 30,000. Then we have the regime of drag resist that exists for a range of Reynolds number between 300,000 and 3 million. For this regime, the separation point of the boundary layer at the back of the cylinder evolves and is often poorly defined. It depends on the surface condition of the cylinder. We do not observe a well-defined vortex wake during this transition. After this transition, from Reynolds equals 3 million, we find a fully turbulent vortex wake. This regime persists thereafter and we observe this vortex wake even at high Reynolds number. Look, for example, at the wake of this island off Japan. The clouds clearly draw successive vortices downstream the island. The Reynolds number is several billion. Let us now characterize this vortex wake. We can do this by measuring the instantaneous velocity in the wake, for example by placing a pitot tube. Here is a typical time series of the velocity that can be measured. The passage of the vortices generates a periodic fluctuation of velocity. Let us note t the measured period and f its inverse. We have here a purely kinematic problem with three parameters: the diameter, the velocity of the flow, and the measured frequency. We can construct a single dimensionless parameter f times L on U. This is the Strouhal number. Based on numerous experiments in a wide range of Reynolds numbers, Roshko has represented the evolution of the Strouhal number with the Reynolds number. At low Reynolds number values, for which the vortex wake is still laminar, the Strouhal number varies between 0.1 and 0.2. Then, a value equal to 0.2 is measured over a wide range of Reynolds number. Between 3 times 10 to the 5 and 3 times 10 to the 6, the value of the Strouhal number depends on the surface condition of the cylinder. Note that this Reynolds number range is the drag crisis range. Once the drag crisis is passed, the Strouhal number tends smoothly to the value of 0.3. In conclusion, the Strouhal number is always of the order of 0.2 to 0.3, except for some limiting cases, such as very low values of the Reynolds number and the interval of drag crisis. What happens for other sections? The case of the square section, for example. A vortex wake is also observed in this case, and the Strouhal number does not vary much with the Reynolds number. It is always about 0.13. Many types of sections can be studied in this way, and the Strouhal number can be measured for each. Here are some examples. We have thus shown that for all these sections, the Strouhal number is approximately constant, and therefore the frequency of the wake is proportional to the flow velocity. This periodic vortex detachment leads to a fluctuating lift at the same frequency, shown on this graph. Let us now consider that we are no longer dealing with a fixed cylinder, but with a structure, which we represent by an oscillator by adding stiffness and damping. An oscillator on which an harmonic force is exerted responds at the same frequency with an amplitude that can become very important at resonance, when the frequency of the forcing is equal to the natural frequency of the oscillator. That is, when the velocity is L times omega naught divided by 2 pi times the Strouhal number. Let us check this prediction with an experiment. On this video is represented the dynamics of an oscillator in a flow. The instantaneous velocity in a plane of the flow is obtained using a particle image velocimetry technique. We can clearly see vortex detachment on this animation, synchronized with the motion of the solid. On the figure below, we plot the evolution of the measured oscillation amplitude and the frequency. We observe that our predictions are verified, except for one detail. In a frequency interval around the resonance, the frequency remains constant. It is the oscillator that imposes its dynamics on the flow and not the other way around. This phenomenon is called lock-in. The phenomenon of vortex-induced vibration is present in many industrial fields. We have observed in the past very important oscillations of chimneys that could permanently compromise their integrity. Double helix structures are now added to these structures to prevent appearance of the vortex wake. Vortex-induced vibrations are used by some artists to create sound works, such as these wind harps by Douglas Hollis. These vibrations can also be very problematic for the stability of offshore structures. This phenomenon must be taken into account for umbilicals or anchor cables subjected to marine currents, for example. But these vibrations can also be seen as a mechanism of energy transfer between a flow and a structure that can be used for energy production, as for example with this concept of tidal turbine of the company Vortex Hydro Energy. In conclusion of this video, contrary to the previous videos, we have considered that the flow has its sound dynamics and that it can force the dynamics of the structure. To simplify, we are dealing with an oscillator forced by a fluctuating lift. In addition, we observe a phenomenon of coupling between the wake and the dynamics of the structure, which leads to a constant frequency over a range of flow velocity around resonance. This is the phenomenon of lock-in.